Good afternoon. This afternoon we have Benjamin Herenschmidt with us to talk about Big Endian and Little Endian and the agony that it's caused us for years. Ben works for the kernel Linux team, presently with IBM ADL Oslabs.
Thank you. So, hi, good evening. Big and Little Endian. It's been a long way, and until maybe 3-4 years ago, we thought that was a problem that was going to be solved, or rather, most people were having a reasonably good grasp of what to do or not to do. In part because we had all those Apple machines out there running Linux and on the PowerPC processor. Now that went away, and sadly, maybe most of the world is back to being Little Endian through x86 and most of ARM, not all of ARM, but most of it. And so Endian bugs have been creeping back into packages, software, the community. The awareness around Endian problems have been decreasing. So I thought it was time for a bit of a refresher. I'm going to talk a little bit today first about what is it all about, then I'm going to describe some of the common problems that can happen within your program's memory. Then I am going to describe a little bit what you can do to deal with Endian issues on storage, files, network, when you exchange information outside of your program. And finally, I'm going to dive a little bit more into IOs and buses and how it's all wired together under the hood. So first, what is it all about? Memory is generally abstracted nowadays as an ordered series of bytes, so an array. The way we address a piece of information in memory is through a byte address. That is, regardless of what the actual data path to your memory from the CPU is. It can be 128-bit wide, which is fairly common, but the logical unit of information that you address in memory is a byte. So naturally from there derives the question of how do you store a quantity bigger than a byte, such as a 16-bit number, in memory? And you can see on Big Endian, the convention is to store the most significant byte first. On Little Endian, the least significant byte first. Similarly, when you store a 32-bit piece of information, you're going to store the bytes from the most significant to the least significant on Big Endian, and from the least significant to the most significant on Little Endian. So far it's fairly classic, and most people are reasonably aware of what's going on. I am not going to go into a big what's better, one or the other. I think it's fairly pointless. There's a few sort of attributes to one or the other that may be worth noting. Big Endian is going to be roughly more familiar to humans from the Western world. It's the way we tend to read from left to right. So if you have a big fat memory dump and there is a kernel address starting with C gazillion in there, it's very easy to spot. So I suppose Linus is not pretty well trained at spotting them the other way around. It's really not that much of a useful thing outside of that. In Little Endian, similarly, it's the area of carry propagation, the order of carry propagation, which used to have small advantages in ancient, very slow microcontrollers or microprocessors. It does allow you sometimes to ignore the type size when you do an access, but it is also where all the problems come from, or most of them. So this is, to some extent, a bad property. There's a few other miscellaneous things here. PDP Endian, don't really want to know about it. There is, probably, we should probably say octet order. A byte technically doesn't have to be 8 bits. And Endianness could represent the order of subgroups within a group of more than just bytes. But for all intents and purposes here, we're talking about 8-bit bytes, and essentially we're talking about byte order of octets. So the one thing to remember is Big Endian is MSB first, Little Endian is LSB first. Why is it called Endian? There's a very good Wikipedia article, has to do with Gulliver's Travels, which I have not read. Yeah, okay. The basic idea, I think, is which end of an egg you crack first. Or you crack to eat the egg, and that lead to war and chaos and mayhem. So what's can go wrong inside of your program memory. And it generally boils down to accessing a piece of information with the wrong type size. So I've made up a simple example here which sort of reflects what is out there. It's fairly common to store a piece of auxiliary information of an object into a void star. You know, libraries provide you with various objects you can manipulate, and you attach a bit of user data to them using a void star. You are more or less expected to put in there a pointer to some custom data structure. It is not uncommon that people are going to shovel an integer in there instead. The moment you start doing that sort of thing, and there is many other cases similar to that, you end up with a problem where here I am going to read that integer inside of my foo function with my printf. I'm going to read it as a char. So I'm going to dereference a char star pointer. The percent in the printf is irrelevant. Whatever is on the right here is going to be promoted to an int by the compiler. The actual problem is the char star dereference. And that integer is defined as an int here. So we assume the int is 32-bit, like all architecture supported by Linux. And we're going to pass a pointer to that int, to that function, which is going to then dereference it as a char. Now we look at what happens in memory. This is the content of your memory, this array here. The question mark indicates something that we haven't initialized yet. You can see here that the dereference is going to look at what in the first byte. So this is 0 related to the value of the pointer. However, what we are passing here is a pointer to a 4-byte quantity. Now in Little Endian, you can observe that it is going to go LSB first, so the 1 is going to go into the first byte, which means that what we are reading is indeed a 1, and you will see your result printed correctly. However, in Big Endian, the 1 is going to end up on the other side of the int, and so what you're going to print here is a 0, and so it doesn't work. This is a canonical example of what can possibly go wrong. Now, you might think, no, it just works on x86, works on Little Endian, Big Endian is not relevant to my business, I don't care, it works fine. This is dangerous. Why? Well, it did work perfectly fine as long as your value was below 255, which we can maybe assume it is. Now look at what happens if I'm inverting my char and my int. So here, I am going to write a char in memory, so a single byte, and I'm going to read 4 of them. So I'm going to read essentially 3 bytes of undefined value. So on Big Endian, it's never going to be right, basically. You're always going to have 1 at the top and whatever else at the bottom. On Little Endian, it might be, depending on what you have in those bytes. Now, so unsurprisingly, there is a lot of zeros in your program memory. There is a lot of zeros on your stack. It is, especially since the way things might be aligned in memory, it's fairly likely that you end up having zeros most of the time there, and it's going to appear to work just fine on x86 until you change a data structure member somewhere or move a variable somewhere in your program, and suddenly that piece of code stops working. In fact, that could also be an exploitable bug. So to some extent, the fact that it never works on Big Endian is a good thing. You're going to catch the bug much quicker. This scenario can typically happen without messing around with pointers when you use unions. The simple example here is you have a union with 2 legs, a short and long. Short is going to be 16-bit, long is going to be 32 or 64, depending on your platform. You are going to read that long, you're going to write to that long using the small leg of the union, and you're going to read it using a large leg of the union, for example. This is always going to work on Little Endian because I put that memset in. So I guarantee that there is no undefined bytes here. That's going to never work on Big Endian. So this is, and this is a pitfall that I've seen commonly. People doing a union of all the possible types they are manipulating, like in an interpreter for some kind of bytecode or something like that, and going to access either leg, depending on what operation they're doing. That's never going to work on Big Endian. Another class of problems that I've encountered a few times is whenever, the whole thing is about weak typing to begin with. And a class of problems related to weak typing is things like IOCTLs, sock option, file fctls, where you're going to pass a data structure that through an interface that doesn't check the type of that data structure. An example that I've debugged fairly recently here, we had a little test program floating around for debugging a socket filter problem in Linux, and the test program never actually worked on my paramachine until I figured why. the program was including this include file, which defines that struct BPF program. Now the BPF is a BSD packet filter. It's not a Linux packet filter. The Linux packet filter is called a socket filter. And this is a structure typically used on BSD or when you use libpcap to define a program for the filter. And so that was instantiating the structure, filling it up, and then passing it to the network stack using SO attach filter. And that worked perfectly fine on Little Endian and never on Big Endian. Why? Well, the definition of that structure comes from the include file, which is not actually a kernel header. That include file comes from libpcap. The kernel, if you look at the kernel source code, what it expects is a different structure called the struct sock fprog. If you compare those two structures, you notice that they are fairly similar, except that the first field, which defines the length of the structure, happens to be an int in BPF program and short in sock fprog. And so, for all the same reason we've seen before, if you write 142 here on Little Endian, it's going to happen to land in the right place, and the kernel will read it just fine. On Big, like this, and on Big Endian, it's going to be wrong. The kernel will read 0. Now, that comes from the fact that the program essentially uses the wrong data structure. But it's fairly common. In fact, I Googled a little bit for SO attach filter on CodeGoogle.com. And I found at least 5 or 6 examples out of the 2 or 3 first pages of results that were having the exact same bug. A funny one here is, so this person is using pcap compile. So he's using libpcap to begin with, to generate the program. And libpcap gives you a pcap attach filter, or whatever the name is, that does just the right thing. It takes that BPF program, turn it into a sock fprog, and pass it to the kernel. But instead, this programmer decided to directly call setSockOpt with a big warning here. Oh, I think something's wrong. I'm not sure what. I'm going to do it anyway. It seems to be working. And slap in the middle a reinterpret cast, which can not do anything right in any possible universe. So this is somebody who doesn't really know what he's doing, I suspect. I thought it was a quite funny one. Another one was this one. Can't find the definition of that structure in the kernel headers. Let's just make it up. And this time with a long. Didn't work very well either. And works perfectly fine on x86 by accident. So another class of problems that I found is reasonably common is marshallers and unmarshallers. Those things will use a printf style format string. So you're going to pass a list of characters that indicate what the type of the arguments are, and then you pass the actual pointers to the argument, and that's going to generate some data stream or file or some RPC thingy. This is a bug I fixed recently in QEMU in the Plan9FS. It was passing here D and B as the format string, which mean respectively integer and byte. It was passing then 2 pointers, one to an actual integer, I didn't write it down, and to an int32. Now the actual and marshaller, the references that as a byte pointer. And so we ended up with something that was going to properly get the LSB on x86, write to the LSB, or write to the MSB on PowerPC. And the effect of that bug was that whenever the guest was trying to open a file for reading, it would be opened in a host with OTruncate, which would have the effect of essentially wiping out the content of that file. So that was a quite nice one. Pretty quick to find. So there is no secret sauce here, just use strong typing. No, you can't say it enough. Use strong typing. Whenever you're casting things, you probably are in trouble. Especially if you start casting scalar type pointers, that is usually really bad. If you really have to, use a pair of accessors. Now you're going to stuff some kind of integer, a reference number, for example, into one of those void star. Make yourself a pair of get and set accessors. So the casting and the dodgy stuff is located in one place. That way, if you get it wrong, it's easy to fix. Now, you don't end up having half of your program doing it right, half of your program doing it wrong in 25 different call sites. Beware of what you do with unions, and beware of hierarchical arguments. Find them in the kernel headers, If you don't find them there, you're probably in trouble. It's okay usually to use them from glibc as well. Don't get them from whatever random library you have in your system. They probably don't match what your kernel expects. Now, an aspect of the problem here that is probably a little bit more well-known or expected by people is what happens on files and network when we start exchanging information with the outside world. It's a fairly simple problem. You do not have to use binary formats most of the time. In fact, text files are really great. You know, they don't have NDNS problems. They don't have alignment problems, bit field format problems, and all sorts of issues that binary formats have. XML might suck, but it doesn't have NDNS problems. It also supports some level of structuring, so it's actually pretty ad hoc for quite a lot of things. Text files aren't that slow. It's most often a fallacy to think that you have a big performance problem with text file unless you are really, really I/O intensive. And no, they are human readable, which means they are developer or debugger readable. You know, when you're trying to figure out what's happening with your file content, you can actually have a look at it and understand what's going on. You can easily insert new things in it. Text files are really good. You know, they are a really good idea. I know there's a whole crowd out there that likes to reinvent everything Unix and make it differently and loves binary blobs, but nah, text files are a really, really good thing, as long as they're ASCII. If you think you really want binary format, you should probably think again. And if you really, really think you want a binary format, then choose one byte order and stick to it. You know, don't get into the whole business of, oh, I have this header that's going to tell me if the file is in big or little endian, and then I'm going to decide whether I'm going to swap or not, depending on who created the file or whatever. You're going to have two code paths. One of them is going to be wrong. You're going to have two copies of the bugs. It's going to be hell. In fact, chances are that with a modern CPU, having a specific test of whether you have to swap or not on every access to the file is going to cost you more than just doing the swap unconditionally. Conditionals can, if they're not predicted properly, hurt your pipeline very significantly. If you are worried about performance, pick up the smallest target you're ever going to have to deal with, you know, that little microcontroller that you really want to run on, and use the NDNS of that as your file NDNS. So that thing won't have to swap. Really, 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 how many times I've seen people trying to have that sort of dual engine file format and just completely screwing it up. Now, if you really are going to do it, try avoiding reading and writing structs directly in and out of your files or your network packets. Try to use streaming construct. You know, have a write U32, write U16, write int, call them whatever you want. You can make them as fast as reading and writing structs, almost. You can have them inline, writing in an in-memory buffer and flushing the buffer all at once. You can do that sort of stuff. You can find much nicer identifiers than the one I've put here, of course, as well. But they are strongly typed. They are going to take care of those problems. They're going to take care of your alignment problems much better than actually writing or reading an entire struct in and out of your disk. They can be slower, but again, there are ways to make them not that slow. You know, they can actually lay out everything in a memory buffer before they actually flush out to disk. And I'm sure there's plenty of libraries to do that out there. If you are going to still put structs in and out to disk, which is what we do in the kernel, because we are bad boys, try not accessing the fields directly, because if you do, it's broken. So make yourself a set of accessors. You know, use size-based accessors like we do in the kernel. They work fine. That's an example of what we do. You know, CPU to LE16 indicates I'm going from a CPU native NDNS to a little endian 16-bit. And really consider if it's a new project adding strong typing. We don't do strong typing in the kernel, essentially because we added a lot of that after the fact, but it is fairly easy to do. And I'll show an example in a minute. Also, forget about bit fields. Really forget about bit fields. In the kernel, we sort of get away with if-defs whenever we use a bit field because we managed to have only 2 types of bit field across the board. We got lucky on that one. Windows is, I think, yet another different format for bit fields. The format of the bit fields, if you are lucky, is sort of in your ABI, but it's really usually a matter of combination of compiler, ABI, and phase of the moon. So be really, really careful with bit fields. An example of strong typing here is now rather than just putting a uint32 in my structure, I'm going to define that file u32. And again, feel free to find much nicer names than I did here. And then you have your accessor to read and write, and you make them inline, so it's all very nice and fast and resolve that compile time. And those accessors are going to effectively do the swapping if necessary. So that uses things that are in endian.h. I'm going to talk a little bit about that on the next slide. But that means that this is going to cause this. So if you fail to use the accessor, you have a compile error. So strong typing here means you basically let the compiler force you to use the proper accessors for the fields in your structure. Now this structure represented on disk data, you use those types for it. And the compiler forces you to properly access them. Now, if you do this, it works fine. Now, there is a few caveats with my specific example. Endian.h, I believe, is a Linuxism or glibcism. I have not found a really portable way of figuring out and doing the endian swapping that is satisfactory. But it's not a big deal because as the minute you put everything in a bunch of accessors, you're going to have what? Half a dozen of them. They go all in one file. You can have a version of that file for Linux, one for BSD. It's very localized, a very small amount of code. You can have inline assembly optimized version for PowerPC that can byte swap with one instruction. You can explode GCC new intrinsic that showed up recently if you have the right GCC version. You can do all sorts of black magic in those accessors. And the rest of your program is essentially unaffected. So, in fact, there was recently, when I was writing that talk originally, because I wrote that talk for plumbers last year, Rob Pike posted a blog post called, I believe, The Byte Order Fallacy, where he made the argument that the whole thing was a complete non-issue. You just had to do that all the time. Now, I might have misunderstood. It's quite possible. But I believe he was arguing that by just using bytes and shifting them into place, you would avoid the endian problems. Now, I can guarantee you that if you use a construct like this one every single time you access a large quantity, larger than 8-bit quantity in your program, you're going to have at least a quarter of them, maybe a tenth of them, depending if you're me, with the wrong shift, inverted two of the indexes. You're going to get them wrong. You're going to get typos, you're going to copy-paste bugs. It's horrible. So just put it in an accessor, which brings you back to my previous slide. You have a fast optimized version that can be your fallback. That will work everywhere, and then you can have better implementation based on your platform. So the whole point, I think, was a big red herring. Do whatever you want, but use an accessor. Also, that can be fairly slow. I remember Dave Miller pointing out on Google Plus that he believes a lot of the time spent by LD to link a Spark kernel was caused by LD using that sort of construct for every IO access to be endian neutral. So, yeah, it's not necessarily a great idea. It works, though. Another approach which we use commonly in the kernel is to use annotations. Sorry, get a bit of water. I've been going very fast. We'll slow down a bit. So you can use something like Sparse, which is this little C compiler front end that Linus wrote a while back, and which we use mostly for static type checking, static log checking and that sort of stuff. It has the ability to annotate types and have a concept of address spaces and things like that. And we can use that, and we do use that for annotating structure fields and things like that that are in a known endian. For example, disk record for a file system, or DMA descriptors for drivers and things like that. And then you can run your code through Sparse, and it's going to tell you whenever you're not using the right accessor. It's sort of the second best solution after the strong typing. The problem is you actually have to explicitly use Sparse. So on Linux you do make C equal 1, which a lot of people don't do. And the second problem is you get a lot of false positive from Sparse. An unfiltered output from Sparse out of the kernel is just completely unmanageable. So you have to run Sparse specifically to one file of your driver and maybe change the command line option to make sure it only looks at the stuff you care about, and still have to go through a lot of false positives. But if you are specifically debugging a driver, it's still very, very useful. In fact, this is how we actually fixed NDNS in XHCI, so the USB 3 controller driver. Intel was very nice. Sarah sent me a card that I could put in a machine at work, and Matt Evans, one of my colleagues back then, basically just did that. He added all the annotation to the data structures that are used by the hardware, by the controller, and then just had to add the accessor whenever sparse told him he was missing one. And it worked. I think the only one other bug we had was a missing memory barrier, which was a little bit more tricky to find. But this is a good way. As it's very good if you're going to fix an existing project. You know, strong typing is nice if you're starting a new project. If you start putting strong typing changes in existing project, the whole thing is not going to build until you fix all the call sites. That might be a bit of a problem, especially if it's a large project. So that way you can go progressively. You know, you can add annotations and then start looking at the sparse result. Yep, I have them. Thanks. So it is probably preferable for new work to use strong typing, but this is a pretty good tool. Another one that is fairly, that has a love and hate relationship with many people is IDLs. Now, IDLs, interface declaration languages, there's plenty of them out there. There's plenty of examples. So the basic principle is you define all of your data structure using some esoteric language, and you run that through some kind of compiler which is going to spit out interfaces, so and libraries or C files you can link or stuff like that. And so you basically use those functions to read or write or send or receive or transform your structures from your C definition to your file format or whatever it is. Now, they are a bit essentially because you have to figure out how they work, you have a new dependency in your build process, you have to write that definition file, they can be bulky. They add a whole new layer to your project. However, if you are doing especially if you're doing a very large project, and you have a lot of that kind of structure to exchange, like you have very heavily RPC related, like Samba is, for example, they use an IDL. This is a very, very, very good tool. You know, it's a bit like having the bulldozer. You know, if you're going to crush an ant, that's not a good thing for you. But if you really want to flatten the hill, it could be the stuff you need. So consider it because it deals with pretty much everything. You know, the alignment problems, 64-bit associated problems. You can pretty much throw everything at it, and it's going to sort it out. But they are cumbersome to exploit. I avoided talking about Marshall and Marshalls as solution because I put them in a list of problems earlier. They do solve other problems. They solve data alignment, layouts, and transport issues and stuff like that. They are very, very handy to use. No single line, and you marshal all your arguments for your RPC call. But they do have that specific problem of not having strong typing. It would be nice if we could have a way to describe to GCC what the format string means and have it warn like it does with printf. But I don't think we actually have a way to do that. GCC hard codes the attribute you can use for printf and scanf, and know specifically about that one. Now, that's a bit of a rough picture of what's out there. I'm sure there are other ways to deal with it, but I think if there was a conclusion here, probably is, text files, really. As much as possible, just use text files. Now, we're going to try to go a little bit under the hood and talk about I/O and buses. I've been going a bit much faster than I thought I would be, so we have time here. So if you want to interrupt or ask something, feel free to do so. I'm going to take an example. I'm going to start with an example. A hypothetical CPU with a very simplistic 32-bit wide bus. And that is going to be connected to 32-bit legacy PCI 2.x, which is a good example. I mean, the fundamental concepts apply to pretty much everything out there. So we have two 32-bit buses connected to each other. What does NDNS mean in the context of an I/O bus, if anything at all? And how does the CPU, NDNS, and the I/O bus relate to each other? So we're going to start from the top. We're going to start with an example, my random storage device. This is a little PCI device, has a bunch of registers, configuration, command, status. And it has a special register, which is fairly common in devices of that kind, which we're going to call a data register. It could be a FIFO or stream. The principle of the register is that you repeatedly read from it or write to it to transport a stream of data in and out of your device. ID does that if you don't use DMA. Often you have this with a DMA control on top of it. The device is advertised as being Little Endian or just PCI device. You're lucky you have a spec. Not everybody has that. And we are going to start accessing it. So the basic thing you're going to do, if you've read Greg Cage's book, you're going to do write-L to access your config register. So far, so good. And that's because that's what you've been told to do. write-L is indeed what you're supposed to use on PCI. There's also the newer IO write 32 from iomap.h. This is going to translate, and that's very simplified because I have removed volatiles, I've removed memory barriers, I've removed that sort of stuff. But it's going to translate on Little Endian into a simple assignment of the value to the pointer. We assume the device is Little Endian, we're on a Little Endian machine, we just write the value. On Big Endian, we are going to swap the value. So far, it seems logical, Big Endian machine, Little Endian device, we swap the value. write-L does that for you. And the reason is not really that PCI is Little Endian, it's more like the vast majority of devices out there are Little Endian. The vast majority, the devices are, the SCSI devices still have Little Endian registers. I'm not talking about the bus. I'm talking about the vast majority of MMIO devices you talk to from the kernel have Little Endian registers. I'm talking about registers here, not your data stream, okay? Data stream is a whole different problem. And we're gonna get to it. So, I want to read or write to my data stream. I want to write a packet or a block. Is this correct to do that? Can I just do a while loop and read L from my FIFO into my memory buffer? Well, if the answer was yes, I wouldn't have asked a question. And this is non-trivial for many people to grasp. Why can't I do that? Now, part of the answer can be found. If you look at the new IOMAP accessors, the header file that define them, you notice that we provide a set of rep variants of them here, which are going to do repeat reads or repeat writes from a FIFO. And there is a reason we provide those, not only to avoid you doing a loop here. It allows you to also avoid too many memory barriers, but mostly because of that comment that I have snipped here and expand here. This is correct, though it's not necessarily very clear for everybody. It says string version of the above. Note that they use native byte ordering for the accesses on the assumption that IO and memory agree on a byte order and CPU byte order is irrelevant. That's actually correct. It's just not very clear. Now there is a way. So the answer is no. You must not byte swap when you access your FIFO. So you can't use read-L or write-L. You have to use those repeat accessors, essentially. Unless your hardware guy is on crack, and there is plenty of examples of these, unfortunately. An example is actually the first TiVo had a byte-swapped IDE bus, which means that everything was completely backward on the disk, which is why you couldn't exchange the disk with, but why? Why don't you byte swap? So, Endianness is not really about the device itself, in fact, or a piece of memory. It's an attribute of a given number, of a given piece of information of more than 8 bits, okay? So, for normal programming registers, the register is both the thing you access, which contains the value, and the value it contains. So the register has an endianness, usually, as a basic of that. It holds a value with an endianness. Fields of data structure that are DMA'd by the device. Those individual fields, not the data structure as a whole, the individual fields in them have an endianness, and so an access that needs to be swapped based on the size of each individual field. You can't have a generic swapper on the data path. You need to know the size of each field to swap it appropriately. So what about the FIFO? Well, the FIFO is actually just a window to a bag, or rather a series of bytes. which is a piece of memory in a way. So if you look at it that way, at the top you have your storage device, which contains this byte stream. Okay? At the bottom, this is what you want in your memory. That's what's going to land in your memory when you read from the FIFO. You read 4 of them at a time, and you want to write them in memory so that they appear in memory in the exact same order. You want each individual byte. Regardless of whether this might be a 16-bit value, that may be little or big endian, you don't care. You want to copy byte-wise that data into memory. You might swap as you interpret it later on. But for the actual transfer from the device through the FIFO, you want that as is. A trick to remember, to understand it, it's a bit of a trick. It's not exactly what happens. In fact, it's pretty much the opposite of what happens when you look at the next slides. But you can imagine that a little endian CPU like x86 swaps data when it accesses the outside world to make it little endian, so from the register. So when the CPU reads from the device, it swaps the value. And then when it writes to memory, it swaps again. And so you got the same stuff that you had. If you want to reproduce that same behavior on a big endian CPU, you swap neither here nor here, because the CPU will not swap writing to memory. So you must not swap when reading from the device. It's a way to remember it. How it's actually wired under the hood. So this is your CPU bus up there. It's 32-bit wide, most significant bytes on the left. What that means is if you're going to write a 32-bit value onto the device, it will appear with the most significant byte on the left, the significant byte on the right. Sorry. The interesting question is, which of those bytes is supposed to be byte 0? Which of those 4 bytes is supposed to land at the smallest address in memory? On big endian, it's going to be the top one. On little endian, it's going to be the bottom one, the LSB. This is really the important thing to remember. Which means that when you're going to connect that to your I/O bus, the one rule that has to be respected, and I know hardware people make crack in the lab, but they really have to get that right, is called byte address invariance. You need to make sure that the right byte end up in the right place. So you look at your PCI spec and it says data byte 0 is in AD720. That tells you which physical lines on your PCI bus contain byte 0. And so that tells you what set of lines on your CPU you need to connect those physical lines. Now, it's interesting because PCI carries both address and data. Address is a semantically rich information. It's a number that needs to be interpreted by the bus. So the address has an endianness, not the data. But the address does. So this, and I might not have drawn that very, very well. I apologize for that. But if you look at how you connect just a data bus to begin with, and it's the same bus that does both, but for now we just bother about data. I have my CPU at the top, my PCI at the bottom. On big endian, so on PCI I know my byte 0 is down there. That's what the spec says. So on little endian, sorry, I need to connect that way because I know my little endian CPU has byte 0 in the LSB. On big endian, I need to connect that way because I know that my big endian CPU has byte 0 in the MSB. So what that means is to connect a big endian CPU to a PCI bus, I need to cross lanes, but only for data cycles, not for address cycles. Because when I want to give an address to my controller, I want the MSB to be in the MSB and LSB to be in the LSB, which is why PCI bridges connected to big endian CPUs internally have a MUX that will swap data cycles and not swap address cycles. And if you have a bi-endian architecture like ARM, it gets pretty funny. But that's really what, but if you care about the data, which is what I really care about on this talk, the lanes are crossed. And they have to be, because if they're not, the bytes end up in the wrong place. Now, from there, naturally derives why we need to swap our device register. Our device registers have been putting its MSB here and LSB here, but because the lanes are crossed, so LSB of the device is going to land in the MSB of the CPU, which is why you need to byte swap. For the FIFO, on the other hand, what we care about is where byte 0 goes. And byte 0 here goes to up there, which is byte 0 as well. So the crossing of the lane means that for FIFO, the bytes are already in the right place. Yeah, so byte 0 went up there. So if I just put everything together, you can see from my device, I have those bytes here. On the PCI bus, byte 0 goes to byte 0 here. I have my crisscrossing of lanes, which means it ends up in byte 0 on the CPU, which is going to put that into memory at address 0. If we go look at little endian, the only change here is that the crisscrossing disappears. Byte 0 goes into byte 0 of the little endian CPU, which happens to be down there, which is going to go into memory up there. So it essentially boils down to memory, storage, bus space. It's just a series of bytes. It's a transport. You only care about endianness when you actually look at a number, an address, a tag on the bus, some metadata carried by the bus. Yes, that potentially has endianness. The actual data packets do not have endianness. They might contain things that have endianness, but per se they don't. Endianness is a property of an item of data, what I just said. The FIFO has no endianness in our case. It just copied to memory. Now, that's roughly it. I was initially planning to talk a little bit about graphics and then realized that we'll never have enough time. Graphics and endianness is a giant train wreck. The fundamental reason for that is that graphics has always pushed the boundary, both in terms of processing speed, amount of data, amount of memory, etc., bandwidth, which means that it's always been a fair game to do whatever you wanted in hardware and software to optimize it to death on a given platform, in the early days at least. And so no real standardization ever survived that. And so it used to be that the pixel format were more or less dictated by a given video card initially on a given platform, and then clones have been copying what the first thing did, and then on the operating system started making assumptions on what that thing did, but a different platform did differently. For example, old macOS only supported ARGB in that order, big endian, and that still went all the way back to today. Big endian stuff in X11 or in Linux sort of expect that sort of format as well, which is not necessarily what most of x86 video cards expect. So graphics is a pain in the neck for that, and we end up with all sorts of odd ways to deal with it. Some ATI cards have endian swappers on the PCI, but that you can configure to automatically swap on access through the PCI, but that doesn't always work very well. Other video cards like NVIDIA, you can specify endianness on the per object basis because they have object-oriented video RAMs, which is pretty funny. It generally doesn't work very well. People have not thought it out properly. OpenGL, arguably, and I've been told that I don't have first-hand experience with it, has a design bug where essentially it defines a pixel format based on the order of the components in the register after it's been already loaded from memory or written to memory, or before it's been written to memory. So a given OpenGL pixel format will have a different memory or file representation depending on the processor you run it on. So it's all a complete mess. And that's one of the reasons why we still struggle today with getting graphic drivers to work properly across endianness. And Gallium has massive endian bugs by design because it was just not thought out. And this is being worked on at the moment, etc., etc. So that's about it. And I'm thinking we have 1.5 minutes left for questions.
Well, actually, we have 7 minutes for questions.
Ah, okay, you have a bit of time for questions. Yeah, excellent. Yep.
Whatever happened to the plain text partition part?
Sorry? Plain text.
Whatever happened to the plain text partition type?
You mean disk partitions?
Yeah.
Yeah, I'm not familiar with that.
Type 88 in hex.
Okay, I am not familiar with that at all. Do you know anything about it, Linus? No. Sorry. I suppose you could imagine a file system whose metadata is in plain text, but it would be a bit painful. Most of the time. Anything else?
Do you have any good tools? Sorry. Do you have any good tools for catching Indian bugs at sort of statically? Because the best way seems to be run it on a big and a little Indian architecture,
Yeah.
but not everyone has that.
So there is two categories. I mean, there is run in a simulator. Run in QEMU is a good way to catch stuff. And we have been working a lot recently into beefing up and fixing up the QEMU PowerPC models as part of the KVM work we've been doing. So you can pretty much now run and install distro, etc. in QEMU, and it works pretty well. Not very fast though. If it's just a simple user space program, you can run the QEMU user space variant, which doesn't run the full system. That's a lot faster. Another way is things like sparse, I mentioned, so the whole annotation thing. If you know that a data structure is shared with a device or is written on disk, or that sort of stuff, you annotate the types, and then you run it through sparse. And sparse is going to catch every place where you are accessing one of those fields without using the proper accesses. So this is really a really good way to find and fix those problems. Of course, you might forget to put the annotation in some places, and nothing is perfect there, but that works pretty well. All right, so I assume that everything love you is no longer going to make any Indian bug in the future.